Assalamualaikum warahmatullahi wabarakatuh and good morning. So previous lecture we have covered method 1, finding DFT by using definition, and also method 2, to find the DFT by using the properties. So this week we will continue method 3 on finding the DFT by using the fast Fourier transform or FFT. So for FFT, as it mentioned in the name, the calculation to calculate the DFT will be faster. This is because when we are using the DFT, the computational time is n to the power of 2 multiplication. And for FFT, the computational time is reduced to n log 2 n. We will see after this at the next slide on the computational time of FFT. So in FFT, we need to find the weight of the symmetrical pair. So this is the equation of the weight, or in the DFT, each of the discrete signal will be multiplied with exponent negative j 2 pi nk over n number of sample. In the FFT, we will see the computational time is reduced because we will divide the calculation into even number and odd number. The detailed calculation will be shown at the next slide. So for example, the weight capital A of and number of sample here, it is equal to exponent negative j 2 pi an. So the general equation is exponent negative j 2 pi. When we multiply with the inner side of the bracket here, this will be given at the weight here. The numerator is at the upper w and the denominator n will be at the lower side of w. So for example here, when we have W1 number of sample, this one is equal to exponent negative j 2 pi. This is the general form, and we multiply with the value in the bracket where the A, the capital A, is 1 and the denominator is number of sample, and we can also return it as Wn. Next example, we have W2 number of sample. So this one is equal to the general equation exponent negative j 2 pi, and then in the bracket we have A equals to 2 and number of sample. This exponential can also be written as another form where the number 2 here is written at the denominator, where the number of sample is multiplied with 1 over 2. So now we have 1 over number of sample over 2. As I mentioned before, the numerator is at the upper side of w, which is 1, and the denominator n over 2 is at the lower side of w. Next is another example, the general form to write the w. We have Wn number of sample equals to exponent negative j 2 pi, and in the bracket we have numerator n, small letter, and the number of sample at the denominator. So what happened if A we change to n plus n, number of sample? So this one is the periodicity properties, where actually it will give you the same value because it is repeated at the number of sample here. So for example, we have n equals to 2 and the number of sample is 4. So 4 plus 2 will also equal to the value of 2. Alright, so for example here we change the upper w is n plus capital N number of sample, and here at the numerator we have n plus number of sample divided by number of sample. the exponential characteristic, the summation here can be expand to two different exponential, where we have the first part is exponent negative j 2 pi small letter n over number of sample, and another part is exponent negative j 2 pi number of sample divided by number of sample. So this one we multiply both part and simplify the equation, where for the exponent negative j 2 pi number of sample over number of sample, this one we can cancel out the number of sample. So the remaining will be exponent negative j 2 pi, and we calculate by using the Euler theorem, cos 2 pi minus, because the sign at the j is negative, negative j sine 2 pi, and we will get the value of 1. So we put it at the second part here, and we multiply with exponent negative j 2 pi and divide by number of sample. So now in the bracket we have small letter n at the upper side and the number of sample at the lower side of W. And next, what happens if the A is equal to n plus number of sample divided by 2? So we just put at in the bracket the numerator equals to n plus number of sample divided by 2, and for the denominator the number of sample is will be divided by the value of n plus number of sample divided by 2. So this is the equation, and like the example before, we can expand the equation of exponential into the multiplication of two parts of exponential. So the first part is exponent negative j 2 pi n divided by small letter n divided by number of sample. Another part is exponent negative j 2 pi number of sample divided by 2 divided by number of sample. So this is the second part. And then we can simplify for this part, since number of sample divided by number of sample we can cancel out. So the remaining will be exponent negative j, this one 2 also can be cancelled out. So it became exponent negative j pi only. Again, we solve by using the Euler, and we'll get the result of negative 1, and we put it at the second part, and then the final answer will be negative exponent negative j 2 pi small letter n divided by number of sample. Last example, what happens if our weight equal to exponent negative j 2 pi k? So now we can see that the number of sample is not shown in the equation. What we can do is, from this equation actually, the number of sample is cancelled out. So the original equation is exponent negative j 2 pi number of sample times k divided by number of sample. When we simplify, we will get the one that at the equation here. So now the weight can be represented as W. The numerator is n number of sample multiplied with k, and at the denominator is the number of sample. Can we simplify this equation? As it written here, exponent negative j 2 pi multiplied with k. So actually for any value of k, for example k equals to 1, this one we will get 2 pi. If k equals to 2, this one will get 4 pi. K is equal to 3, this one will become 6 pi. So when we have the even pi, so for even pi, actually the value will be the same as exponent negative j 2 pi. Okay, you can change the value of exponential into exponent negative j 2 pi, exponent negative j 4 pi, and exponent negative j 6 pi. When we do the calculation, the value will be the same, which is 1. So actually for any value, any real value of k, when we multiply with 2 pi, we will get even. So when we get even pi, the final answer will be 1. That's why here we can simplify the weight and k, number of sample multiplied with k, and the lower part is number of sample will be equals to 1. So this is the weight for the fast Fourier transform. So actually, how can the fast Fourier transform can be calculated faster? Because the weight is only calculated a number of sample divided by 2. For example, if we have number of sample equals to 4, the weight that we need to calculate in the fast Fourier transform is W0 and W1. And if we have number of sample equals to 8, so how many weight that we need to calculate is number of sample divided by 2, which is 4. W0, W1, W2 and W3. Okay, so again, this one you can see by yourself. So what is the meaning W0? So it means that at the numerator, the value is 0 at the bracket, in the bracket, and then you can solve one by one. So for example here, when we have W2, so at the numerator we have times 2 with j to pi, and then divide by number of sample, and we will get, when we simplify the equation, we will get exponent negative j pi over 2, and then you can calculate by using the Euler, where we can have the value of negative j. Alright, so for the FFT, in our case we will use the radix 2. Okay, and for the radix 2, this is the important equation where the number of sample equals to 2 to the power of small letter m. M refer to the number of stage. Okay, and this is what I mentioned previously. The computational of fast Fourier transform has simplified, or has been reduced to number of sample log to number of sample multiplication, compared to the conventional DFT, where we need to use n to the power of 2 multiplication.